In this short video, we will look at the physics of the photoelectric effect. Now, the photoelectric effect is so called because it involves photons, or bits of light, and electrons, negative charges. What the go is with the photoelectric effect is you have a metal surface and you shine some light on it, and you get electrons coming off the surface of the metal. Like so. Now, the interesting thing is that sometimes, depending on the colour of light you've got, you can have as much of that colour light as you possibly can, and you still won't get electrons coming off the metal. It only works for some colours or some energies of light. Here we have some orange light, and that's just not working for our metal surface. We're not getting any electrons off it. Oh, but look, we've changed colour to red, and now we've got some electrons coming off. And if we increase the intensity of our red light, as in we add more red light to the beam, then we find we get more electrons. Let's try changing colour again. Let's go for purple. So, hey, look, we've got an electron, and not only have we got an electron, but it's moving. Increase the intensity, and we get more electrons that are moving. So, from these physics experiments that were originally done in the early 1900s, we've learnt that it is the colour of the light that determines whether we see any electrons coming off the metal surface. And if our light is more intense, so it's brighter, then we'll see more electrons. But if it's still the wrong colour light, there still won't be any electrons. And finally, we've seen with just a few of these examples that the colour of the light also affects whether the electrons that are released have any energy or not, whether they're moving. Remember, the electrons that were released with the red light, we just got them. They weren't going anywhere, whereas with the purple light, the electrons were moving. They had some kinetic energy. So now we're going to put that all together into this radical idea that the light itself is made up of particles called photons. And these photons have an energy that is determined by their colour. But when we say colour, what do we really mean? Well, I guess colour is an easy place to start, because that's the kind of light that we're familiar with, the light that we can see, red, orange, yellow, green, blue, violet, indigo. But there's also light or electromagnetic radiation that we can't see on either side of the rainbow. So some names that we give this invisible light include things like ultraviolet, which is responsible for sunburn, comes through the hole in the ozone layer in the atmosphere, and infrared light, which is also known as heat, basically. If you have an infrared camera, it's looking at hot things, basically. And in fact, there's more kinds of light still, and so we have a whole spectrum. And it turns out X-rays are one of these kinds of light. And beyond X-rays, you've got gamma rays, which are more powerful again, more energetic. And on the other side, beyond infrared, you've got microwaves, radio waves. And that's a brief rundown of the electromagnetic spectrum. So yeah, basically one end of the spectrum is low energy radiation and the other end is high energy. And so this is why colour is linked to energy. But colour's really a human construct. What's really going on is that the light has different wavelengths. Yeah, okay, I know I just said light's a particle made up of photons, or light's a stream of particles called photons, and I've just claimed they have a wavelength as well. Okay, and the next thing that's going to blow your mind is that all these kinds of light travel at the same speed, the speed of light. Now, if light's a wave as well as a particle, its wave nature means that, yeah, it has a wavelength, it also has a frequency, and the frequency multiplied by the wavelength is the speed of light. So, yep, there you go. The speed of light, c, is equal to the wavelength multiplied by the frequency. Okay, and we've got that high energy equals short wavelength, low energy equals long wavelength. So, if you've got short wavelength, it means you must have high frequency. And similarly, low energy, low frequency. So, we've just had a brief explanation that high energy light has high frequency, low energy light has low frequency. So, energy is proportional to frequency. So, we say that energy E is equal to H multiplied by F, where F is the frequency. Now, H is a special something called the Planck constant. Now, the Planck constant is pretty special and it crops up all over physics, and it's intrinsically linked with this idea that you can package stuff up. You can chop stuff into particles and it can act like a particle. Or a single particle is called a quantum. And this is where quantum mechanics kind of really starts. So we're not going to do more quantum mechanics, but you should know that this is some deep physics that we've got going on here. The Planck constant is, a constant, so it has a fixed value. And this is its value, 6.626, and some more decimal places, multiplied by 10 to the power of negative 34 joule seconds. So anything multiplied by 10 to the power of negative 34 is a really, really small number. Really small. And basically that's referencing the idea that you're only going to see this behavior where stuff can be a wave and a particle at the same time on really, really small scales. And it's important not to forget the units at the end of this constant, joule seconds. So we know the units of the Planck constant. What are the units of frequency? So frequency of something is defined as cycles per second, and it's number of cycles per second. So cycles doesn't have a unit, it's just a number. But per second, that's a unit. So we have our Planck constant in joule seconds. We're going to multiply it by something that is seconds to the power of negative 1. Remembering that taking something to the power of negative 1 is like saying 1 divided by that something, so 1 divided by a second. Then we can cancel those seconds out. We had a second on the top, a second on the bottom. Cancel them out, and you're left with joules. So you get joules, the unit of energy. Started with the Planck constant in joule seconds, multiplied it by frequency, which is cycles per second. Seconds cancel out, you get joules, you get an energy. So that's a way of like double checking that your formula is sensible if the units match up like this, because we wanted to get an energy which is measured in joules. So you actually see joules around the place a lot. The energy of your food is measured in kilojoules. So 1 Tim Tam is about 450 kilojoules. So the joule is a unit that we tend to use when we're describing sort of macroscopic everyday objects. We know what it means. If someone says 450 kilojoules, we're like, yep, that's a Tim Tam. So we've been talking about electrons and things which are way, way smaller. And it's really hard to say how many joules an electron has. I mean, you can do it, but it's going to be a crazily small number. And when numbers are either really small or really big, humans struggle to make sense of them. So we come up with another unit that still is a measure of energy, but it's more appropriate for the physical situation, and that unit is the electron volt. And why is it called an electron volt? Well, long story short, if you had a battery and your battery was 1 volt and you had an electron and you sent it from one side of your battery through your battery to the other side, then that electron would have gained 1 electron volt of energy. 1 electron, 1 volt, 1 electron volt. But how big is an electron? Well, it's a negative charge, and it is the smallest negative charge you can get. You can't chop an electron in half. Doesn't work. So it's known as an elementary charge. You can't get smaller charges than 1 electron. So the amount of charge on 1 electron is 1.602 multiplied by 10 to the power of negative 19 coulombs. Coulombs is the unit of charge, represented by a capital C. And simply, the energy of 1 electron volt is that energy of 1 electron, 1 charge, going through that 1 volt battery. So it's the charge on the electron multiplied by 1 for 1 volt. Oh, one moment while I do something just to make it a bit clearer. So a volt is defined as joules per coulomb. So we can rewrite the capital V as capital J divided by capital C. And then you can see that we've got a C on the top, a C on the bottom. They're going to cancel out. And so then we're left with 1.602 times 10 to the negative 19 multiplied by 1 joule. Energy. Oh, we've found our unit of energy, joules. So we've just defined what an electron volt is in terms of joules. And we represent electron volts with the symbol little e, big V, electron volt. Super stuff. So, key things you learnt in this video. The energy of a photon, a packet of light, the energy of that is the Planck constant in joule seconds multiplied by the frequency in cycles per second. And we also call this unit of frequency cycles per second. We also call that hertz. And look, it's got nothing to do with car rentals, okay? But yeah, hertz, and the symbol for hertz is Hz. So don't worry if you see a frequency described as being, 100,000 hertz or something like this. All that means is 100,000 cycles per second. And we also learnt about a new unit for energy, the electron volt. And we also saw a bit of a story of how people started thinking about light in this way, shining light, getting electrons off a metal surface, but wondering why this depended on the colour of light you were using and why how many electrons you got depended on the intensity of the light. And then that led to this idea of light being a particle as well as a wave. Don't forget the electromagnetic spectrum, everything from X-rays to radio waves and more. And yeah, anything can be a wave and a particle at the same time.